We're going to take a brief look at problem 45. In problem 45, the block of mass m travels at v1 in the direction shown at the top of the smooth slope. We want to determine its speed and its direction when it reaches the bottom. So first of all, notice that this is a smooth slope, and we learned in chapter 14, when you have an object sliding on a smooth slope, well, friction doesn't do any work because there's no friction, and the normal force doesn't do any work because it's perpendicular to the direction that the object is traveling in. So the only work done on the block in this problem is done by the force of gravity, for which we can use gravitational potential energy. So the first thing that I'm going to do is find the speed at the bottom of the incline, and the speed is only changing because of the force of gravity. So the speed changes because the height of the block changes. So from our work energy conservation law, work done by non-conservative forces in this problem is 0, so kinetic energy plus initial gravitational potential energy is equal to final kinetic energy plus final gravitational potential energy. So I have that here, and I have kinetic energy initially, that's 1/2 mv1 squared. We're starting at a height h, so let's say the datum is here, and I have initially mgh for my initial gravitational potential energy and 0 for my gravitational potential energy when I get to the bottom of the incline. At the bottom of the incline, the kinetic energy is 1/2 mv2 squared. I have mass in every term, so I can cancel those out. And then to solve for v2, we multiply both sides by 2, then take the square root. Now, if you look in the x direction, so that was shown in our diagram here, because the surface is smooth, I don't have any forces acting in the x direction. If I have no forces acting in the x direction, I have no impulse in the x direction. If I have no impulse in the x direction, then the momentum in the x direction before is equal to the momentum in the x direction afterwards. And so the momentum is the mass times the velocity. The mass is staying the same. And so if the momentum before is equal to the momentum afterwards, the velocity before must be equal to the velocity afterwards. And this is true in the x direction. Well, I know that the velocity in the x direction, by looking at my picture here, would be the sine component of my velocity vector for v1 and for v2. So the x components are equal to each other, then the sine components are equal to each other, so v1 sine theta 1 is equal to v2 sine theta 2. That comes from the conservation of momentum in the x direction. But I found v2 in terms of v1 using the conservation of energy, so I can take that and put it in here, and then solve for theta 2 by bringing my v2 over to the other side, so divide this by the v2 that you have here, and then take the inverse sine of what you have here. That should be the inverse sine of this, and that gives you theta 2, and that's problem 45.